All right, hi everyone. We're here for another perspectives in AI seminar. Today we have a very a key guest here. We have Claudio Pinhanez, a person who's been very important to the center from the beginning. Claudio was the deputy director for many years here, but he's now an independent AI scientist, innovator. People know Claudio's trajectory in AI from the 90s, I suppose, working with many different issues at MIT and IBM Research. And he's here today to talk about LLMs, non-determinism, and some of the key issues that are important to AI at this moment. Okay, Claudio, thanks. Go ahead.
Thank you, Fabio. Hi, my name is Claudio Pinhanez. I used to be a deputy director of the Center for AI. I used to be part of IBM Research until December. The lab was closed, so now I'm an independent AI researcher. If we can have but it's a great pleasure to be here. It's a great pleasure to be back and to be doing this seminar in some work that was mostly done when I was still part of IBM Research with a team from there. There's some new stuff. Fabio talked a little about my trajectory. As I said, I'm independent AI science, which means it's a good way to say I'm unemployed right now looking for opportunities. But anyway, that's where I am. I'm also going to be a visiting professor here from June. Well, for many years, for almost 26 years, I was part of IBM Research, first in the US, then here in Brazil. But I was also a professor here in the early 90s at the University of São Paulo and so on. But my area of work is the intersection of AI and human-computer interaction. That's always where I've worked and I've focused, although what I'm going to talk here is a little more technical, a little more on the AI side, although not everything. Just so we are sure we are speaking the same language, I'm going to use the term generative AI or GenAI to refer to basically two kinds of models. Models to generate text based on transformers. A classical example, I do something like summarize the text. You get a text, it produces something. We all know that. We also use this term for diffusion models, often used for image generation. What I'm going to talk today, I don't think it applies necessarily to diffusion models, and especially I haven't tested with diffusion models, so maybe it works also there. But diffusion models have a very different structure, very different kinds of problems than LLMs and so on. So where we are in GenAI, okay? And one way to summarize where we are is GenAI produces good outputs for most users most of the time, which is a very optimistic way to say GenAI sometimes produces bad outputs for some users sometimes, okay? And we know that. And often those bad outputs are referred as hallucinations, which I think it's a terrible term because it's vague. And also, in my view, it encompasses different kinds of problems, different kinds of issues. And today I'm going to really focus on some studies we did on consistency. Okay, but before that, I'm going to have a more general overview of what I think is a fundamental problem in the technology of LLMs. And my understanding, this is intrinsically associated to the way transformers are structured and work, okay? First, I'm going to address the issue of most of the time, the fact that they sometimes produce bad outputs, okay? And the first important thing is, if we have a technology that sometimes produces bad results in an unpredictable way, the whole idea that this technology can be trusted is flawed in principle. If we cannot guarantee, and here I'm going to contend that I believe this is intrinsic to the technology, but if we cannot guarantee that they can always produce outputs within some boundaries, within some level of errors, we cannot use this for many applications that require trust. We cannot use this for medical decisions, not without human supervision. We cannot use this for customer service, because that requires precision, that requires consistency. There is a lot of legal requirements around this kind of technology, okay? So we have to move away from this idea that we can create a technology that's trustworthy in itself to another thing is, because of that, we cannot do automation. We cannot put direct in contact with people if we cannot trust it. But the way I look at it is saying, oh, because of that, we should not also use this technology. No. What we should work on is how can we use this flawed technology in a trusted environment, in a trusted context, which may be domain specific, which may be context specific. Think about medicines. Medicines are not safe. Most of them are not. But we create an environment for each medicine that says when it can be used, who can take that medicine in other conditions, what problems are expected, and we use them every day. It's not something new that we take a technology that has problems and find ways to properly use it and to safely use it, in spite of being sometimes very dangerous. Okay, and I think, of course, this takes more work and time. We have to specific work in every application, and we have to look in every case. But I believe that's where we are in GenAI. We are in the situation where every application requires work on how it can be used. You cannot use it blindly in many ways, okay? In particular, I'm going to talk in the first 10, 15 minutes of this presentation about a particular issue that's related to this most of the time, correct, which is non-determinism. The fact that in generative AI, especially in the case of text, we cannot expect to have the same answer to the same question, which is very simplistic way to define non-determinism. And I understand that in computer science, determinism has a much more precise definition. I'm not going to work at a level, but just say that's the problem. Okay? Well, okay, so about a year ago, I was in Japan. I was completely lost in time because of time travel, of time zones and different. I went to ChatGPT and asked, what day is today? And I said, okay. And I said, oh, does it understand the different ways to ask this question? We are starting at a time to work with consistency. So what if I start to ask in different ways, which are totally equivalent? Okay. Oh, very interesting. This is not scientific, okay? But five of the 10 answers were wrong. For a very basic, well, a basic question that a system should translate to some kind of agent, go to a clock, get the answer, convert the time zone, get it. So for some reason here, that's fifth line, it was Thursday, it said it was Tuesday. And I say, oh, maybe it's because of time zones. No, there's no way that the same date is 2 days of the week at the same time. Can be separated by, could be Wednesday if you are in a different place, but not Tuesday, okay? At some point it was giving me time, not date. Okay, sometimes it was, the Tuesday was 2 hours, so this is common. And what we start, when we start to look with this, we start to look at being consistent in this sense that asking the same questions, the same question many times, is very, and getting answers, some right, some wrong, is very common. And I'm going to show you later how common this is. But let's first think, imagine that you are asking harder questions, more important questions. What are safe cholesterol levels? Who can vote in this election? And it tells one person you can vote, and the same person has the same rights, you cannot vote. Inconsistency is really a serious problem. Okay? Or what time my flight departs, or so on. There are critical questions that requires always the same answer, independently of how small changes they may have. Okay? Why is that? Well, if you look at the architecture of a typical transformer, which is behind of the systems, there are two basic sources, in my view, of non-determinism, there may be other ones, and we can talk, but there are two basic. First is, some of you may be familiar with this. I'm not going to explain this, but basically, when you have a transformer, you have the prompt, it's encoded in, it goes to this encoder, which is this stack of 12 levels of this thing, weird thing, 12 or more levels, and creates a mathematical representation, a space representation of the question. Well, small variations in the prompt may produce large variations in this embedding, what's called embedding. So this is the first, what would be similar questions can go to different places, maybe very different places in the embedding space. And we know embedding spaces are weird. We know that. But the most common, in my view, source of non-determinism is that transformers are sequential systems. They do this embedding, you including in this machinery inside this huge neural network of the decoder. You put the prompt, it generates a probabilistic distribution of the next token, let's say the next word. Then it randomly determines that based on these probabilities, what's the next token is. Put in the prompt, go again, and so on. So at any of these iterations, you start to go different possible forks in this large tree of answers. And this essentially, since the final answer is one leaf on this huge tree, is essentially, this is clearly non-deterministic. Of course, you can, if you decrease the temperature, the model tends to choose the highest probability. Okay. Another source of non-determinism is also errors of rounding, issues of particular issues of the hardware being used, and so on. So it's part of it. And the only way to decrease this that normally people have in their hands is to decrease the temperature. But we know that if you decrease the temperature of inference temperature, which is the level random there, the accuracy goes down with that. Okay, so a code model is not good. That's why, otherwise people would always run in code environments. But a code model is not good. It's not as good as a medium temperate model. And we can talk a little about why is that when we start seeing some others. So that's reality, okay? So I'm going to make a hypothesis, say, which is more like a way to look at this. What's the problem here? Okay, one mathematical way to look at this problem is that GenAI models are not locally continuous functions. What I mean by that, oh my God. Now I'm going to enter horror terrain for some people. I'm going to talk about epsilons and deltas in calculus for a brief moment for people who have had that bad experience in life, okay? But basically the idea is it's continuous, meaning, so here is my space of inputs. Of course, it's not bidimensional, it's 50,000 dimensions or more. Here is my space of outputs, which is the space of sequences of words. Let's put this. So what I would like is that if I have a neighborhood in my space of outputs, of sentences that are similar, answers that are similar, I can find a neighborhood here in the space of embeddings that everything inside this neighborhood I know goes there. This is to be locally continuous. I'm asking too much. I understand that. For people in math saying, maybe locally bounded is enough. Maybe locally bound is enough for this output. But let's say they are not. Why do we know this is not the case? Okay. But before we go there, why this is important? Why locally continuous functions are important? And I'm going to make here the case that they're essential for doing good engineering. You cannot do good engineering if you don't have local continuity. Imagine this thing. Okay. Okay, I'm going too fast here. Just a moment, let me go back if I can. Okay. Why do you need? Imagine that I'm building a bridge, okay? 20-meter bridge. I do some level of structural analysis and say, okay, it works. And then someone says, oh, it has to be 21 meters. You say, I can use probably the same structure. I'm going just to stretch a little. I mean, that should work. Of course, if the bridge was 30 meters long, 50% more, I probably could not use that. But the fact that I have local continuity allows me to stretch things a little. But more important, allows me to find species-wise solutions for my problem. Say, if it's 10 meters long, the structure can be like this. If it's 15, it can be like this. And I calculate that and interpolate in between. And this is very old. This is from 1614, 500 years ago. This is a table of logarithms. That's how people used logarithms at that time, interpolating pre-computed results. And this is essential in engineering because it allows you to be predictable. Okay, you have things that I know work here, they work here, the middle should work. Allows you to be consistent. Things that are close go to the same place. Allows you to do quality control. Because you know if you sample your input space in a small enough interval and see that the outputs are correct, you say, oh, the whole space is correct. If it's locally continuous, okay, all the neighborhoods will go to the right place. I can do quality control using sampling. In fact, the fact that we use quality control in GenAI with sampling without locally continuous functions is a major source of problems. It's why it's so hard to guarantee safety in these systems. Okay, so this little complicated issue here is, do you want this locally continuous to be in the space of embeddings, which is a mathematical representation of the inputs, or in the space of meanings of those inputs? And ideally, would be in the space of meanings. But for a moment, let's forget that. Just say, okay, I expect the two to be the same. I know they are not. But let's just simplify the arguments from now on. Okay. Okay. So the question is, how discontinuous are those functions? How bad is this model? How bad those? How small stuff produce different stuff in the other side? And well, we know it's true because we know that prompt engineering works. What's prompt engineering? You're doing small disturbance locally to produce better outputs. you have a prompt, you include a story about who is talking about that prompting, and it improves the quality. And things like that. The fact that prompt engineering works shows that they are not locally continuous. Okay, so let me give an example. Playing yesterday, write a catchy slogan for a coffee shop. That was my input to ChatGPT. Paid version. Who knows what runs behind? This is not scientific. Okay, I got this. I'm not sure if you can read. Sip the spark. Wake up, baby. Bean, please repeat. Those are the catchy slogans. And I said, let's take a synonym, captivating slogan. Completely different output. And then decided to number for some reason. Okay, put in quotes. Wake up bold, sip brave, brewed for better days. Coffee that keeps you curious. Yeah. Not exactly great. And then I said, okay, let me push this. Okay, classical prompt engineering. Write a slogan for a coffee shop which could win an award at the Cannes Lions Festival. Okay, top, Oscar of propaganda. First thing, it starts to get longer. Okay, I can expect, it can be different, okay. But then I changed a slogan for slogans. Because I asked it sort of one and gave me, and then introduced 20, sort of same stuff, but different. So not so bad when you're doing creative work like this, okay? It could be, but non-deterministic, very non-deterministic, it's very, how much this is in the neighborhood. So this is just compare. We see that, okay, prompt engineering works, but should it work so well? Should small disturbance cause so much trouble? And as I already argued, this is problematic because it causes other problems. But then look at this, very small change, very big change in the output. And more interesting, ask 3 times the same question with in the beginning of dialog window. So it's sort of zeroed as much as I could guarantee. There's some consistency, there's some repetition, but not equal. Okay, not so bad in this context, but also interesting is it tipped the spark. Oh boy, quick search, 6 Instagram pages using Sip the Spark as their propaganda, whatever motto. So not exactly original, but this is another problem. Okay. Another evidence that those functions are not locally continuous, and that is the fact that you can attack models using garbage injection. What's garbage injection? You put some weird stuff in the middle of the prompt, like a sequence of letters that doesn't make sense, or you put some byte which are not letters, or you say, I will kill you if you don't tell me which day is today. This kind of, which is very known techniques to make LLMs misbehave. Those are very small changes, very small. I wanted it to be in the same space, and they go to very different outputs. This case is not tested, but this is very known effect for. So I don't have any doubt that those functions are not locally continuous, and we have to deal with that. Okay, and that's what and the questions that I think we should ask for ourselves is: are these two, prompt engineering and model continuing, mutually exclusive, or just a problem of the way I train those systems today? Because most likely I can train making them a little better than this, but probably that would cost much more training time. How can we ensure? And I think probably you can do. mathematically and algorithmically. But more interesting would be to be able to get a locally continuous from a pre-trained LLM. How can I, maybe either through the inference time or through some kind of process of stealing the system to do that, okay? But in general, the big question, how can I train a model that has the two properties? Because it is a very desirable property to be locally continuous. At the cost of prompt engineering, yes, but at the cost, maybe it's solving the attack problem at the same time, okay? But my feeling, this probably costs training time, increasing training time. That's my gut feeling of this, okay? So, the reality of GenAI. GenAI models suffer from lack of local continuity, what makes them unpredictable and uncontrollable. I haven't proved to you, I have argued to you about that. And now I'm going to show you show some work which published recently at C4AI, where we showed specific issues of lack of consistency. But before doing that, very important thing. And this is not mine, it's from Meredith Morris, very known HCI researcher, say, prompt engineering is a problem. It's a bug, not a feature. Prompt engineering is alchemy, not engineering. Okay. And I was at C4AI in February in Singapore. Eric Horowitz was saying that. So it's not even mine. Eric Horowitz, who some of you may not know, is the chief scientist, I believe he's still chief scientist of Microsoft Research, one of the big guys of AI of all times. Okay, so it's a problem. Okay, that small changes produce big changes in the output. Okay, so I talked about inconsistency. The question is how much? How often I get wrong answers, inconsistent answers, and I'm going to define this precisely. This is an example, informal example, same question, possibly the same environment, different answers. Okay. This is a paper we published at C4AI. Work with Paulo, Cassia, Marcelo, Iago, back at IBM Research. And the idea was to systematically measure how, in this case, small models up to 8 billion parameters, and I'm going to tell you why, how much they are inconsistent in a replicable and precise way. Try to measure that. Okay. So, but the idea is, I'm going to ask the same question a certain number of times, exactly the same, with exactly the same environment, and see how much it changes the output. Okay. And we did that, to be sure there was no noise in the measurement. We did that using two benchmarks, two multiple choice benchmarks. So there's only one answer that's correct. And that can be easily determined by just saying, what's the output? Is the output letter X? Okay. This is an example of a benchmark that used for medical. It's a very hard benchmark. In fact, it has very complicated cases of emergency rooms and very technical terms as outputs. And in this case, we ask 10 times this question, same environment, same temperature, for 4 different, I think there's a mistake here, but 4 different medical models, okay, models that were trained in medical structure. And see, in this case, MedLlama, which is the best model of its class, 70% accuracy in average, as reported in the paper. Okay, 5 times right answer, 4 times D. and half of the time was wrong. Biomedical was good, was consistent. Biomistral was consistently wrong, and this other one that's wrong there was all over the place. Okay, so so one way to look at this is saying, okay, imagine that every line of this bar graphs is one question. Okay, one question. Each bar is one trial, full trial. Okay, so if we measure accuracy, we don't see much variation along each trial. Okay, 0.73 in the case of Medellama plus 0.004, very low variance. So they seem very similar models. A little bit. But when we look at consistency, and we do that by aligning, here I aligned all the answers to the same question. Medellama has about 11% of answers that is not consistent. Biomedical llama, 40% are not consistent. So these two models have two very different strategies to answer this question. We know students who play that model. If I don't know, I guess. Okay? Which is very successful. It does very successfully. In average, as good as the other way. So guessing is not a bad strategy. And in fact, we believe, we don't have proof, that they learn to be guessers because that avoids local meaning of a question. It's a good learning strategy for a benchmark. Okay, but let's go on. Okay, so in the paper we define formally what we call answer consistency, and basically we use this analogy to an old idea in computer science, which is the idea of oracle guessing. So I'm not going into details here, but basically by doing this kind of analysis and this kind of computation, we say, if you want the model to be sure, what we call 0.999% sure or 99.9% sure, it has to answer the 10 questions identically. Then you are sure at that level. Let's relax. I want it to be 99% sure of it. This is my measure of how consistent. You ask 10 questions, 100 questions, only one is not consistent, okay? And this can be measured by saying, try 9, you have to produce 9, in average, 9 or more identical answers, okay? Which will be what we're going to do. Using 0.99 consistency, 99%, see the difference between these 4 medical models. In gray is how much is unsure. You have, in case of Med alpaca, 81% unsure. It has a accuracy that's, I think, 50-something%. It's not a bad model in average. It's a terrible model in consistency. Okay, so yeah, I'm bringing a new problem. It's not only accuracy. The problem is consistency. Okay, so we define this precisely what I mean. A question being right, a question being wrong. Being right, saying the most common answer is correct, because it might be consistently wrong, which is good. It's not bad. It's not often, and it might be consistently correct, which is even better. And we represent consistently wrong as red, deep red, consistently right as green, deep, this bright green. And you cannot see, but the grays have different levels for things that are correct but not consistent, wrong but not consistent. But look at how bad this is. Okay? And the way we represent this, because those two things is by 2 numbers. The first number here, we call it the RWS, the right when sure number. Okay. So takes the answers that are sure, that the model's 10 times the same thing. The deep color stuff, how much of that in percentage is? When it's sure, how good is the accuracy? That's RWS we put here. And the second number is how often is sure. Okay? So 8-9%. So for instance, the first bar of the graph, 8-9% of the times it's sure. Good. And of this 8-9%, 76%, 77%, it's right. Look at the one on the right. 90% of the time is sure. It's almost never. And when it's sure, most of the time is wrong. Really bad model to be used. If you need any level of consistency, it's a terrible model. It's not a bad modeling if you look into accuracy. That's the problem. Okay. So what he did. Okay, experiments. MedQA, this medical data benchmark. We took 4 models. We took 4 models, fine-tuned. We also took the base models where they are fine-tuned from. Didn't expect it to do well there, and we also, because we were at IBM, we tested with granite models. All these models under 8 billion. All these models run locally under our control, controlling temperature. So it's repeatable measurement system. Okay, so this can be done by anyone. Those are open source models. Everyone can do this. And so here we have, for each model, 3 bars, so different temperatures, 0.3, 0.5, 0.7. Okay, and so 3 for the first model, 3 for the second. And these are the fine-tuned. There's the base models. First thing, the base models are a lot more sure. So expected. They don't understand medicine. But we saw huge difference. We saw in some models the temperature made a huge difference. Some it didn't, like in the best model here. And some models are just not consistent at all. So it's a problem. It's there. For granite models, we saw basically the same thing. These are not medical models, so it was expected. But we saw one thing that was very interesting. When you look at the accuracy when sure, okay, when I'm sure how much, that was very similar to the overall accuracy. In fact, this is this line here. This is the accuracy when sure. This is the average accuracy. So it's not that being sure not affected the overall accuracy. No, it had the same behavior. And that what makes us think that the model was really using consistency as a way to deal with hard questions, and learn that guessing is more interesting than locking itself in an answer for some questions. This is a hypothesis we didn't test. Another thing we saw, okay, if the number of sure, how often is consistency, it changes according to the temperature as expected. What we saw is that for lower temperature, we could get 64% consistent. So 1/3 of the times the models were inconsistent. It's terrible. Think it this way. Ask 3 times a question, chance of getting an inconsistent answer in you ask 3 questions, 1 is going to be answered inconsistently. Okay, imagine that you are talking to customer service, that every three questions you ask tells you something different from the other customer that in exactly the same situation. So We saw that for all models, for all 8 billion parameter models or less. And this is very consistent. Why we didn't try with larger models? Okay, we didn't find any open source model at that time which was larger, medical, which was larger than 8 billion, which was open source, so we could. So we decided to do that with that test with another benchmark, which is ML Redux, which is a general knowledge benchmark, very commonly used. We took a special variation. It is a 4-choice benchmark. It's a little easier in that sense. We tested with small models, including DeepSeek, Llama. These are genetic models, not fine-tuned. We tested with what we call medium models, which are models up to 70 billion parameters. This is far from the big guys, but the big guys are very few are open sourced, and we didn't have machines to run those. This was done with, I believe, 24 GPUs to be inference time, which is. So we did these experiments also again for these 2 classes of models, small and medium. Granite models, different temperatures, 0, 3, 0, 7, and 1. And well, as expected, these are general knowledge questions, it more likely to have variation. But what we saw is for the small models, a lot of inconsistency. But with the medium models, no, it was not there. Said, it's a problem of small models. Unfortunately, not. We didn't see in this experiment. We have very strong reasons to believe that those models are contaminated by this benchmark. What do you mean, strong reasons to believe? You ask the question without the multiple choice answers, and it gives you the right answer. Okay? We didn't provide the answers, it provides you the right answer. And we saw that happen. So medium models tend to be more recent, they are more contaminated. We didn't have time to run these experiments with non-contaminated models and so on. But for us, I mean, this shows these guys probably are safer to look at this moment than those guys, but those need more attention. Again, granites, same thing, and we again saw this correlation between the right when sure, the accuracy when sure, and the average accuracy, not as strong and only at a lower temperature. But again, this is a much harder benchmark than the other one, much less precise and so on. But we saw the same level of 1 in 3 questions had issues at lower temperature. That was consistent around the same level. Okay, so we did a similar experiment, which I'm going to talk about, playing with the answers, changing the order, including not one of the above instead of a wrong answer. We try to play with different kinds of variations in the answer, and we saw very similar results. We have this paper in archive that talks about that. So I'm not going to. So basically, this is not only for exactly consistent. Small changes in the question also didn't produce small changes in the consistent answers. So the reality, what you can take, what we saw for small models as they do not answer consistent the same question about 1/3 of the times. This is bad. I was expecting when I started the experiment to be 10%, not 1/3. 1/3 is unbelievably low. And a lot of times this may be perceived as hallucination when it's just a model guessing, because guessing is good. Hey, everyone has been a student here, or some are probably still. Guessing is good in a multiple choice test when it's not punished. And they discover that. Those machines discover that. That's a good strategy. It also avoids that you get trapped inside the local minima of a question, in the wrong side of it. It's a good way to increase your average accuracy when you think about that. Okay? So, going back. Okay. Oops, sorry. So I'm going to take 5 minutes to go. Sorry, I'm playing with. Have a quick look into the other issue, which is the most users, not most time. But at this point, what I think this is the really take-home message, saying we haven't looked enough at the issue of consistency as one possible case of hallucination, and how much that affects our sense of accuracy. And particularly, the plan, if the lab hadn't closed for us, was to try this with no multiple choice questions. But of course, then you introduce the error that you have to compare answers. Then we would deal with that with statistical means and so on, okay? Because then you have error in the measurement. We don't have error in the measurement here, okay? But I think that's a very important question that we didn't answer, is what if are open-ended questions? Is that at the same level, is higher, or for the same question? Or 10 tries, same question, blah. And of course, that would require different definition of what is consistent than the one used that's based on multiple choice. Okay, I'm going to take 5 minutes to talk a little about this issue and talk about two projects very quickly, and then we can have time for questions. Okay. The fact that the GenAI does not produce bad outputs for some users, sometimes often, sometimes or most of the time, says, okay, it's not inclusive. Those systems are not inclusive. If they are not, if they should be for all users, especially if it's not for a particular group of users that have, for instance, people of some race, people of some gender, people of some ethnicity, and so on, which then includes, that brings ethical issues on top of this. But how do you deal with that? And we know that. We know that answer for 40 years in human-computer interaction. Most computer systems are not inclusive. And how we deal with that? We do inclusive use of AI. We look at that community and make it inclusive for that community. And the way we do that with that is we work with them. There's no other way. We know this is textbook HCI. Okay? And particularly, it's also textbook HCI, this way of saying this. You don't build a system for a community without the community. This is a motto that comes from the accessibility community from 90s. Don't talk about accessibility without including people with those issues, and works. We know it works. And in fact, in these two projects that I'm going to talk about, that's exactly what we did. We work with the community to solve issues of inclusivity. So this is not we know the solution of this problem. It's just that I don't think that's done enough. And it's important to talk about that. So the first project I'm going to talk about, also again at IBM, it's a project we did for 2 years trying to create a text-to-speech voice for IBM, English, American English, that could be recognized as an African-American person. Oh, is it easy to recognize an African-American person by voice? Yes. One word, hello, you get 80% of agreement that on the race of a person in the US. Okay, this is used for law, inclusive, for issues of discrimination in court. So it's very known result. So what we did, How are we going to deal with this? This was internal project of IBM. So we didn't have any African-American person in this group. Why not? Because there was no one speech-to-text person in IBM Research from African-American descent. Did that stop you? No. You find the community. We found people from the African-American community inside IBM, brought to them, explained the project, got authorization to work into this. They told us it was a good idea. And every important step of the process, they were together. And they were fundamental for us. So we did auditions. We select candidates for audition. This has to be recorded, done on top of someone's voice. Helped us select, helped us judge the results, select one candidate to record 15 hours of studio time. Then we built this voice, different versions, we evaluated with them. Then we tested with a larger system. We discovered that there were some issues. They helped us understand some issues that we found in those voices, and which is in that paper that I pointed to. I don't have time now. And now it's an IBM product. And hopefully we can have sound.
Most U.S. English text-to-speech professional systems produce voices recognized as white speakers of standard American English. The goal of the project was to create a state-of-art text-to-speech, TTS, expressive voice, which is recognized as an African-American person and fluent in African-American vernacular English.
How many of you recognize this on African-American voice? Says, oh, everyone's going to say. What? And I leave to this the paper. White people have a hard time. African-American don't. Recognize African-Americans' voice, speech is also dependent on race. That's also no result. That's one thing we learned from them. In the beginning, we got these weird results about white people not recognized, thought we had a problem. They said, oh, that happens all the time with us. Okay, white people cannot do that. I said, huh. White people, I said white, it's no African American, I need to be precise. Okay, so another project very quickly, very dear project of mine, project we are doing. There's another example of involving the community. This is processing of indigenous language. Tom is here, Tom is part of the project. And there's a project where we are developing digital writing tools for communities in the Amazon, in the Rio Negro. And very quickly, and what we did, we partnered with a major federation of indigenous organizations in Brazil. And we followed their protocols of how to engage with the community, and we did all the steps. We went there, we talked to them, we explained, and they told us what they needed, and we worked with them, and we found a way. And the way we found to work with them was to install digital classrooms there, so we could work with them continuously without disturbing, so we could do development in a way that was easier for us, easier for them, and at the same time, we brought them something they wanted, which was a digital classroom. This was tablets, Starlink, solar panels, and we ran last semester 4 workshops a week of 2 hours with the students there, about 100 hours of work with them. This is very unusual, and we developed together. At the same time, we told them things together. We told how to use a digital school, how to both teachers and students. And well, there's a project that we are looking for partners, so it's a little for continuing this year. We are continuing to July, but we need funding, we need structure, we need a lot of stuff, but especially funding at this point, okay, to continue this. Because what we want is to expand this to a lot of other communities there. But anyway, the reality is, if you want inclusive GenAI, we have to work with the communities directly. Okay, there's no way out. And I don't think for the AI community this is clear at all. That's why I'm saying something as someone who comes from HI, it's obvious, but it has to be there. Okay, so we started here. Okay, GenAI doesn't produce bad outputs sometimes for some people. What take over from this? They suffer from this lack of local continuity, and that makes them unpredictable and uncontrollable. That has to be solved. That's a problem for computer scientists, for machine learning. Maybe it's not solvable. Maybe, I mean, you have the random guessing that's happening in the sequential process there. That has to be controlled in some way. But you could have a loss function that includes consistency as penalty, lack of consistency as penalty. My guess, that would increase training time considerably. And that's why probably it's not used. But it will eliminate the problem of temperature, possibly. Don't know. Prompt engineering is a bug, please. Let's have that very clear. You are, when you're teaching prompt engineering, you are putting bugs in the heads of people. That's where we are. But there's no way out. There's no way out. But it's a bad practice. Okay? Okay? Think about models are not consistent. We have only evidence for small. I don't have reason to believe that's different for the others, but evidence just for these small models. And if you want inclusiveness, you have to work with the communities. It's not from top down. Okay. Anyway, what I'm trying to give you here is this idea that there are fundamental issues in this technology, in the way we are using this technology, that this goal of a generic trustworthy AI is probably not achievable, and probably intrinsic to the models we are using. I'm not sure if it is also true for diffusion models. I believe it's probably true, but it's much harder to measure there, but it's okay. And this idea that, okay, is that a problem? No, it's just, it involves us more work to make it work for every case. We've done that. We know how to do that in engineering. Okay. Okay. So basically, instead of trying this generic stuff, although we should measure, we should try to fix, we should focus right now on make it usable, make trustworthy use, case by case, which is more expensive, harder, but hey, that's where we are. Okay, thank you.
There's time for questions. Let me start.
Okay.
So
questions on the microphone.
All right. So
an improvised microphone.
Not very elegant, but so let me try to differentiate between. I think it's very nice to make the point that even without considering the temperature, it's non-robust, because there are many things that are, you change a little bit and then it creates a big problem. And but I guess mathematically the function, if you're using like ReLU, mathematically it's continuous. I think the problem must be that when you're making the selection of the token, then you break you make a non-continuous decision at that point. So, and that blows everything. But let me take that point aside. So let me just focus on the temperature. In your experiments, you're asking the same question. So the temperature is not really the point of these experiments. So is this a question?
We did for each temperature, fixed temperature for.
Okay, so that's my question. Why do you change the temperature since you're asking the same question?
Because we get different levels of consistency depending on the temperature. Let me show you.
Okay, even for the same very question. Okay.
Even for the same very question.
Okay.
See, let me try to bring that for you.
So why do you think this? Why do you think these students are guessing? I guess their point is that it's a good strategy to guess. Is it so good? I mean, I hesitate.
I used to guess. It's a good one if you don't know the answer. If you don't know if you're right, that's a good strategy when you don't know if you're right. And remember, during training, you're not looking into you don't know what happened last time. Which maybe that's one thing you have to change in training to deal with this. Okay, but look at this. It's so MediQA, granite. See, these are different temperatures. Okay, it's huge variation. But also within different models, there are huge variations for the same temperature. Okay. And then you say, okay, let's go to 0.01 temperature. Accuracy goes dramatic. If it was not the case, you always would run at 0.01. So it's a big hack. Okay. This whole idea of temperature is a big hack to increase accuracy levels that became widespread use in the industry. But it's a classical hack you do in a paper, right? You say, okay, in a machine learning paper, classical hack, right? Sequential, in this case of sequential machine learning. But now it's alchemy, became part of an alchemy system. There is something interesting that also Eric Horowitz said at C4AI, which I thought was very interesting. He said, the interesting thing about LLMs is that they work so well. We don't know why they work so well. They shouldn't work so well. They do. And partly, I think, because there are brilliant engineers behind this stuff, and behind the training, and behind this. There are really brilliant people that makes these terrible things work and get these results. But it's bad engineering. Let's assume it's bad engineering. You don't build a system. I mean, we know that non-determinism is bad. That's computer science. My God. Come on. That's the worst thing. That's the devil's area of computer science, right? We know, but it's helpful in these situations. Okay? Maybe I was a little strong on this, but okay, go ahead.
One more question.
Well, hi. I'd like to just make a few remarks, actually. The thing about being another proof that GenAI is not, local, continuous, is that of psychophancy, the act of pleasing the user. Since those GenAIs try to please the users, the answers do always change, depending on how the user's, saying how he feels about what he's asking the GenAI about. But differently from prompt engineering, that it's a bug, psychophancy is a feature of those models. It's embedded in those models, and because of that, the companies that try to make their models less sycophant, they have to change everything behind it to make it a little bit less reactive to the emotions of the user. Mm-hmm. So it's not actually a bug, it's a feature.
Well, we have to be, I think in the sense that I'm putting here, it's a bug, okay? Because this bug in the sense of not being locally continuous. The fact that it's trying to please the user is something, it shouldn't matter for the same question, assuming that the goal is to give a correct answer or a creative answer and so on. But the fact is those systems, we have reasons to believe, are trained to please the user because that's good economics for the companies. I mean, I haven't seen formal proof of this. It's probably the case, okay? So in that sense, for the people who built the systems, that's a feature. For us as users, I think it's a bug. Okay, it's a problem that it tries to please us too much. As most situations, that's a bad thing. We can discuss that. But let's, in this moment, say, still, pleasing is still bad engineering. It's the emperor has no close bug. Let's put it this way. It's similar to that. It's pleasing everyone, but not what's supposed to be said. Okay, but I think the models are trained for that. Okay,
And maybe
that's more complicated ethics than
taking advantage of, thinking of principles of AI differently from requiring explicability to be a principle shouldn't being, continuous be a principle of AI. You also mentioned that a more consistent model should be more accurate by itself. So shouldn't that be a principle?
Explicability?
No, I mean, people always, argue about explicability, but I think maybe being locally continuous or being more, consistent is a more important principle rather than explicable.
I think it would be lovely if those systems could be explicable. They are not. That's one problem with the whole explicability. Nobody knows how a neural network works. In the sense of why it goes to minima and not to other ones. To the point that what we know even is that the space of local minima is fractal. It's even worse, it's chaotic. So we don't know how those things work. So to believe that we can explain that is just dreaming. Sorry, you cannot. These things will never be explained. I'm asking for here something much smaller, but I think the goal is to have something that can be engineered. We cannot do engineering with those systems if they are not locally continuous. Again, it can be relaxed, something a little simpler. It's about being bounded, compact. I mean, if you look at topology, maybe the word is compact here. I'm still guessing this, but it's much smaller what I'm asking here than explicability. And I think explicability is a crazy goal that somehow it's a wishful thinking, but not for most machine learning systems, most of them, particularly not for neural networks. Okay, even one layer neural network we cannot explain. Okay, go ahead.
Yeah, I have two questions. One is the problem of consistency is, do you think is a general problem, or it's like it depends on the problem that you are asking or solving? Because, for example, even in a human, if I ask you like a question right now, and I ask it like 2 years later or 2 days later, the same question, you're probably not going to give the same answer. Like even human are not like that. So why a machine that simulates like kind of the behavior of human, it should be consistency?
I think that the answer about that is if we sell those machines as inconsistent from the beginning, I'm okay with that. But they are not portrayed that way. And people don't regard machines as inconsistent. They believe, wrongly in this case, that machines are always giving the same answer. That's what people expect from machines.
Yeah, but that's like not the way that they were built, because
no,
like in the deep level, like AI is a computer program. So usually a computer program should give like the same answer for the same input. But in AI that is data driven, it's not like that. So it's probability.
Well, that's not how most people will look at those things. Okay. They think, how many of you expected 1/3 of inconsistency in this model? Even you are hard CS guy, okay? But if you ask most people, most users, I don't have any doubt that they will say, of course he's going to answer the same, especially because we never ask 10 times the same question. Let's say these machines, okay? No, we zero ask for each question, okay? So I mean, we try to be a very safe protocol, and but we always start with the same seed, okay? There's the technical details, but have to be careful because if order, and we know that order matters and this stuff, but But we try to be, and that has a cost. We increased a little the inference cost, but we pay the price. This was probably, I don't know, probably 2 days worth of experiments, 2 weeks worth of experiments in 20, I think 12 to 20 GPUs. It's a lot of, takes time to do this kind of test. Think this way, each temperature, about 1,500 questions, 10 times, blah, blah, blah.
Yeah, just a second question. In the protocol, I'm not sure if I catch in the presentation, you use it like the vanilla LLM, or you use like tool calling and external resource?
No, we took we run the models ourselves, because otherwise we cannot guarantee that it could be sent to different models in different machines. It could be cached. After 5, the system says, "Oh, asking the same question, let me answer." So that's why I could only do with open source models. Open source in the sense of the parameters were open source, and we took exactly how they came from Hugging Face.
And do you think that the context should change the answer? That should change the consistency?
The context, what do you mean?
Context, like the context, I mean external resource or tool calling in the LLM.
I don't think APIs are safe. I don't think I mean, when I'm refereeing some papers and I see people using API calls, I say, this experiment by definition is non-replicable, because you don't know what's happening behind there. So often what I ask them, do it more times, do it different times. So, but you don't know if they're changing what's in the back without you knowing. And this is also a very known problem when people start. I mean, this reminds me when people are doing work on search in early 2000s, and when Google appeared, it became a nightmare for evaluation, because they couldn't have access directly to the Google engine, but just through the API. But you deal with that. You can deal with that. We didn't want to. I mean, this, because we knew this would be a no-no for many referees for good reasons. Okay, we have to be sure. That's why we try to be safe. Same machines, same, not same GPUs, because this is the cloud, but same class of GPUs, all this, because we know this can change. I
guess we have time for a final question, maybe. Paul?
Thank you for the talk, Claudio. My question, if I understood well, so the inconsistency was due to the sampling procedure, right? The same sampling procedure. The same input.
I don't know. I guess.
But you always fed the same input to the models.
Exactly the same input.
You just changed temperature.
But at the same time, I mean, they produce answers in the same, or the correct answer is blah, blah. So in fact, it's letter X. So it's just if you look at this, if it's sampling, it's just that sampling of the token of the right answer. Okay? And sometimes they produce more stuff. Mm-hmm. But that should mean, if the sequence shouldn't be. And sometimes they had variations in the trailing question, although that was in the prompt, that they should answer that way. We wanted to have some context before giving the yes, but we gave them that. The details are in the paper. Okay? So you could say that non-determinism may come maybe just from one sampling. I'm careful with that. We didn't
I was
check for that.
To ask you that, because there is also the second problem of the prompt engineering that I talked about, where you change the input. Do you think how it could measure that inconsistency?
What we did is, we did this other paper where we changed the question by, we take the multiple choice, we would randomly change the order, or we would put none of above among the wrong answers. And we saw very similar stuff. A little more. It was a harder problem. And also the issue of changing the order has to do with the memorization. We know that some of the systems that they learn, they have guessing from They learn from positional stuff. Okay, so those are huge learning systems. Everyone who has really worked with a machine learned system probably has had this experience, that suddenly the model starts cheating on you. How many of you have had this experience, of you who train models? So that somebody, this model is cheating. It's giving me it's giving me what I want to hear. I'm been tweaking the parameters, and it starts to give and it starts to learn with me as developer. Okay, that's a very interesting moment. I remember the first time I had that. Okay, they can learn, find weird ways to please you. Yeah, think it this way: the goal of a machine learning process is to please the developer. When it stops, when the developer is pleased. So those are machines who please developers. Those are algorithms that please developers. And they find any way they can do, as much as they have a structure that's complex enough. And these guys have a huge structure behind them. Huge, huge, huge. Completely not explicable. So we know that they memorize. We know that they hide stuff. We know that they find correlations. We know, I'm not sure you have seen, they know that they can learn how to create a random number generator inside their systems. It's not there initially, but they learned, they produce small pieces of it which are number generators. There's a very interesting paper about that. Yeah, so much stuff. There's, 150 billion parameters. You can waste it in any way you want, as long as you please the developer. That's the name of the game. Please the developer. Right? Thank you.
All right, thank you. We have time now for some coffee and more discussion with Claudio. Thank you.